like that? I something?
iCarly.
4, 3, 2.
No.
What?
It's like 2, 4.
Sorry, you're recording.
Is it a 5?
Yeah, 5, 2.
You got it. Start again.
I thought it went fast.
Dang it.
No.
I screwed it up.
3, 2. I can
3.
I like iParson. Happy place. iParson. I better be quiet because Apple's probably listening in on me. They're thinking like you stole our line.
They're gonna copyright claim
I
you
was trying so hard
on your own website.
They're gonna get there, okay?
Yes.
Maybe they'll give me a bunch of money.
For restarting the
Wouldn't that
show.
be cool? Hey, guys, example 4. We were talking about this idea of a limit yesterday. We said, what's a limit and what's it look like graphically? And we said, you know what? Limits are going to come up when we start talking about places where discontinuities might show their face. Kids, first of all, take a look at my function. Cosine of x over what?
X.
Why is my limit as x approaches 0?
Because if x is 0, your denominator is
0 would make that function undefined, wouldn't it? So let's pick on this. And we're going to do a couple other examples. So it says, estimate this limit how, kids? How does it say to estimate this limit?
What? Graph.
Graphically. All right, let's get into my favorite tool in the world, Desmos. And Desmos says,
Parson,
yeah,
isn't that discontinuous graph that John got confused about? Is that what it's going to look like?
kind
Right
of.
on the
It
y-axis,
could.
is it gonna be
It
a
might.
circle?
Let's check it and see. Let's see what this looks like. I'm going to show you another one that's goofy. Is that cool? All right, let's make sure we're first of all probably in radians. Is that okay, guys? Are we in radians? Looks like we are, right?
Yes.
Okay.
Down,
What am I typing in, kids?
Cosine x.
Divided by what?
X.
Whoa.
Snap.
What?
That's a pretty neat looking graph. I'm not going to lie about that, kids. That's pretty neat, right?
I understand.
Let's talk about this right here. First of all, where did our discontinuity happen at?
0.
So we're looking at values right around the x value of what?
0.
Now, does my graph kind of come together at 0, or is the right side going way up and the left side going way down?
Just like.
The second one.
For
Are they?
infinity.
Does it look like where there should be a discontinuity, the parts that are left and right of 0 look like they could just jump and meet, or are they going way, way far away from each other?
Way.
They are not even in the same zip code, are they?
No.
So when that happens right here, you say, you know what? Well, we think it's either positive infinity or negative infinity. Either way, I don't know which value it's starting to converge on. So therefore, in a situation like this, I would say graphically, because there's like an asymptote, the left side's approaching positive infinity, the right side's approaching negative infinity. There's no one value I can certainly say this is what it's approaching. So I would say the limit here does not exist in this situation. You understand why something would not exist there. I don't know where to stop. When I get really close to 0, am I up here, or when I'm really close to 0 on the left side, am I clear down here? I don't know. Isn't positive 0.001 and negative 0.001 the same distance from 0? Okay. But this is going way down here, isn't it? And this is going way up here. Are those the same values?
No.
Not today, not tomorrow, not ever. Okay, so what are you going to say about that limit? It does not exist. So let's write that. Okay, so but we're going to try another one. This one here does not exist. Okay? Do you understand what does not exist looks like graphically, kids? All right, let's try this one then. Should we pick one that does exist? Let's do this. Let's do the limit of, how about this? Should we change cosine to sine? Let's go sine of x over x. So in this case right here, kids, talk to me. What's x have to approach here? What's the problem?
0.
Okay, let's see what this looks like, okay? So let's see what this looks like graphically. You ready for this one?
Yes.
Oh, goody goody. So I'm just going to go up here and change cosine to sine. Is that okay with you guys? Ooh. Now this one here is saying, all right, I'm going to type in x equals 0. Is that okay? Does it intersect up there? Oh, wait a minute. It doesn't intersect. I'm going to do something here quickly. I'm going to zoom in around 0. Is that okay? I'll get rid of this one.
Would it not be okay?
Well, the graph looks like it's there. Oh my gosh. Oh my gosh.
Whoa,
What does it say there?
undefined.
Is that good or bad?
Good.
Okay, so let's talk real quickly about this, kids. I know it's undefined there. It's an empty spot. Let me see if I can zoom in on that a little bit. If I go just a little bit to the left of it, it's just getting really, really close to. I'm going to zoom in even more.
One.
0.
Looks like it's converging on what?
One.
But at 0, it's not defined, so it's discontinuous, right? How about the right side? What's the right side seem to getting really, really close to?
1.
What do you think the limit is here?
1.
1. Okay. Is it saying the value is 1 or the limit is 1? You can't say the value is 1 at 0 because at 0 it's undefined, right? But I would say its limit. The graph is going to... What this limit is kind of saying, guys, is this. Listen here carefully. Yeah, I could say that... I'll take a screenshot of this. It's saying that this is open. That spot is open. It's not there. But what it's saying is as I approach that spot, that undefined spot from the left, or I approach that spot from the right, we're getting very, very close to what y value? 1, right? So we won't say the value is 1. We can't say the value is 1 because it's undefined there, right? But I can say the limit is approaching what? All these values just to the left of it and all these values just to the right of it are right around 1. So we say the limit of that function is 1. Okay? Let me ask this question. Do you understand graphically the difference between a limit not existing and one that does exist? And what that looks like?
With like continuous and discontinuous?
It's kind of like where the discontinuities are. So we know there's a discontinuity here, right? One graph went clear up here on the left side and way down here on the right side, right? Okay, but this, the left and the right, are both kind of pinching at a point. And when
So does it have to deal with the y's?
Yep, the limit right here that we're trying, we're basically saying my graph, it's undefined here, but if I was infinitely close to that graph, both the left side and the right side would kind of pinch at around a y value of 1. Make sense? Okay, so that said, let's go back to, I need to get out of this. What did we say the limit was there? You want to try another one graphically and then tell me what you think? Okay. So that limit is at 1. Okay. Let me pull a good one here quickly from the book. Is that okay?
Let's just make one. I'm gonna make one right now. See if we can do one.
Okay, how about this? What if I changed, all right, what if I changed, what if I changed this to maybe x minus 2, kids? Down here in the bottom. Oop, that's not good, is it? How about x plus 2? Maybe that'll work. That's not going to work either, okay? Let me find a good one, okay? Aren't those graphs kind of neat? Those were the flames I was going to put on my new Chevy Spark yesterday. Did you guys see my new Chevy Spark yesterday?
You got an electric car?
Huh?
You got a new car?
No. I was driving the Chevy Spark, though. I look like Shaquille O'Neal in a Buick.
Stole that from
Oh,
me.
I go home and try.
Fun stuff.
At least 5 times.
All right, let's try this one, kids. How about...
Well, personality is weird.
All right, how about this one right here? Where's your problem spot, kids?
Okay.
Where's your problem spot?
2.
Oh, come on.
X, 0.
0 is my problem spot. So maybe if I come down here, maybe this is another way to explain it. If I type in, we know the problem spot is at x equals 0. Okay? Let me ask a question. Does the graph that's red pinch the green line, or does it run asymptotically to the top and the bottom of it? It pinches it. So what y value am I pinching at?
2.
2. So right up here it says 0, 2. But keep in mind, that's on the green graph. Let's get that out of there. If I'm on this graph right here, if I go to 0, what's it say? Undefined. So I would say the limit as x approaches 0 on this, it's not saying x is equal to 0, it's saying x is getting really, really close to 0. That from the left side of 0 and the right side of 0, your graph is about what value? 2. Okay? Are you okay with that? Okay? Now, we're going to look at different ways of finding limits as well. Again, we're doing it as x approaches 0. And when I say x approaches 0, we're looking at really, really small values that are so close to 0, but it's not equal to 0. Like if I did this, let me do this. X equal, you ready for this? 0.00001. And if I go through here, okay, now that's not x equals 0, is it?
No.
Okay, what is this rounding to when it gets to that limit? 2. If I go x equals, let's go to the left of 0. How about negative 0.000? Do I have 3 zeros or 4 zeros up there in that person? Okay, there's that line. Let's get on the black line and see where it crosses my graph. It's going to round to what value again?
2.
2. So are these two graphs right at 0 or not?
No.
No, but left of 0 and right of 0, they both converge to what value, or limit out at what value? 2. Okay? Are you with me on this? So if something pitches, the limit pretty much exists. If it runs asymptotically to the top and the bottom on one side, the top on one side, bottom on the other, then you will say the limit does not exist. Okay? All right, so I'm going to pause this here and get you guys. Okay, ready?
Okay.
Sweet. All right, so graphically, I think we're okay with this, all right? Let's do limits numerically. You want to do that? Why is H a problem here, kids?
That's why I'm thinking it's A.
Oh, yeah.
0.
Okay,
Oh, well.
so we're going to have a discontinuity at what value, kids?
H.
Okay, and then H is going to be what value when it's discontinuous?
0.
So we want to estimate a limit, and this is how you do it numerically, all right? I'm going to do this. I'm going to put 0 in here, and I'm going to leave this alone. Put these values in for H up there. And then we're going to do this over here. All right, I need some volunteers to help me out here. Anybody want to do that? Okay, we want to know what this, if this pinches at a value or not. So guys, we know at 0, we've got a problem, right? Would you agree with that? So I'm going to leave that spot alone. So what I'm going to say is we're going to look just to the left of 0 and just to the right of 0 and see if both values around 0 to the left and right of it trying to pinch at some value. So what I need someone to do is this. Who would be willing to put the negative 0.001 in, or the 3 zeros and then a 1 in up here into this function for me? Who would be willing to do this value into that function? Okay, Maddie, you've got this one. Who would do this one for me? Aubrey, the second one. I need someone to do positive 0.001 in their calculator for me.
I can.
Maddie Frush, you got this one. And who wants to do the last one for me? Got it, Sybil? Okay. Punch them in your calculator. Let's see if we can see a pattern or anything evolving here, okay? Because this is going to be pretty important stuff here.
Did you get it right where you're...
Are you ready, Aubrey?
Yeah, so I had the negative 0.001, and that's 7.999.
So the second one in?
Yeah. Wait, I was wrong.
So you're in here.
Yeah.
Mine was the first one, and I got negative 7.999. But I don't know if it's supposed to be negative.
Okay, we got the same thing. I got 6.999, but mine's not negative. It was this one.
I think I did mine wrong.
Maybe you forgot to put the negative on the bottom of it. You divide.
How about this? I'll tell you they're all
I have
very
to
positive.
divide
Is
it?
that all right? So you said 7 point. Yeah. Now divide by. Are you good now?
Wait, what do I have to divide by?
What are you gonna put in for h? Whatever this h value is.
Oh, sorry.
Mine is just like only.
I understand now. Yes, it's positive.
7.999.
Yes.
That's what mine is too.
Mine's 8.0 is
Kids, I have a question. 7.999, 8.00001. What do you think that we're converging in on or pinching around? 8, okay? Numerically, it looks like we're pinching right here at 8. So we think by this table that this is going to be right around what? 8, okay? Now, I want to show you something here. Finding limits. We're going to use algebra to find limits of this function right here, and this is how this works.
What's the name on the, file today?
I don't know, Paul today. Okay, here's the deal. When we're doing things algebraically right here, we think that this is going to converge on what value? 8. We think the limit's at 8, even though it's undefined. When you use algebra to find limits right here, here's what you really do, kids. You're really going to go ahead and say, all right, we're going to plug in this function right here that we're trying to find limit for. They basically want you just to go ahead and expand everything. So let me show you what this becomes. This becomes a limit as h approaches 0. So to solve this algebraically, here's what's happening. Okay, this h is something that we can kind of have drop out. So let me show you what happens here. Kids, if I would expand this right here, 4 plus h all to the second power, do you agree that this becomes 16 plus 8h plus h squared when I FOIL that out over here on the left? 4 plus h times 4 plus h. Let's just FOIL that out. What's the 4 times 4 going to get you, kids? 16. Inside, outside. Inside's 4h, outside is 4h, so plus what? Plus h times h, which is what? So do you guys agree that I FOILed that out correctly? Okay? So this part that we FOILed right here is this. Now, here we're going to subtract the 16 that's out here, and then this is still all over what, kids? Okay, let me show you what happens here. Up top here, after I expand this out, what's the 16 and the 16 do to each other? So what we're essentially left with is the limit as h approaches 0 of the following. What are we left with?
Why were you able to add that 16 on top?
Subtract the 16 or add this one?
Subtract.
Because
Like,
that
you
was
just,
part
like-
of the original problem right here.
Oh, wait.
That minus 16 is that minus 16 right there.
Okay.
And the 16 out front came from 4
yeah.
times 4 when I square that.
That makes sense.
Good there?
Yeah.
Okay. All right, so what do I have left up top, kids?
8h.
Over what?
Over h.
Now, what's really unique about stuff like this involving limits is the following, kids. What does this h down here do to this h right here? What does this h do to one of the h's up here? So I can take an h out here, here, and it goes away in the bottom, right? It's kind of like factoring an h out up top, and then they just go away, right? So what we're essentially left with, kids, is the limit. As h approaches 0 of the following function. 8 plus what? H. But h is essentially what value almost now? What is h approaching? Well, I pretty much go in there and say, guys, h is pretty much 0 right here. What value are we going to be really, really close to in the end?
8.
8. Okay, so this basically is going to limit out at 8. And isn't that what we found up here numerically, kids? Isn't that what we found up here numerically, by putting values really close to 0 in there? So this here basically is saying, well, what happens if you would expand this? So do you understand the 4 plus h squared are the first 3 terms here? Do you understand that minus 16 was part of the problem up here? And then h is still down there. But what did the 16s do up top? They went away. So maybe we can figure this out algebraically. Said, okay, well, it became this. But this is the same as, watch what I do. Can I take an h out of the top here, kids? So this would be h times 8 plus h all over what? Well, what's this and this going to do to each other? Right? And it looks like you're in 8th grade up there, but it's 8 plus h. But h is essentially what value, kids? So what's essentially nothing plus 8 going to limit to, or get really close to? 8 is the limit. Okay? Now guys, this concept's not going to go away. It's not going to go away in the next section, the section after that. We'll talk more and more about this concept, but this is a big idea. I'm going to tell you right here, this idea right here is pretty much the focal point or the foundation of why calculus was invented. How do you find slopes over very, very small intervals? Or what is my limit over a very, very small interval? Or what's my rate of change when we're talking about distances that are infinitely small, or as h approaches 0, okay? All right, so I think there's one last page, is that correct? Guys, I want to back up. From yesterday, do you guys recall what an instantaneous velocity was? Is AB an average velocity or an instantaneous velocity?
Average.
This is an average, right? Okay. So let's talk here. I really like this example. Example 7, visualizing rates of change. This is pretty cool. Okay. First of all, it says the graph of y equals f of x is shown below. It says arrange the following in order such that it's ascending order, where 1 is representative of the smallest value and 6 is the largest value. Now I need to speak to you about one of these, okay? Actually a couple of these. I want you guys to put a star by A, and a star by B, and a star by C. Okay? Notice this notation right here. See this F and this little apostrophe and then A right here? That means F prime of A. What this is saying is, what's the slope? What's the instantaneous slope at point A? Alright? So I'm going to take a second and draw some of these in here for you, just to get you an idea of what it looks like. Some slopes in here. I'm going to put an instantaneous at A. Is that okay? Is that slope pretty steep or not very steep at A? I'll do my best to make this work. You guys okay with that being a slope at A right there? Okay. If any of you want a ruler there, go ahead and get one over at the front of the table. How about B and C? What's going to be true about those two slopes? They're going to be pretty steep or pretty flat? Good here? So this one here is going to pretty much, B is going to go here. What's going to be true about the slope of B and C? Which one's going to be less steep? Get a different color here. C is going to be pretty flat, isn't it? Got to be a line of tangency, right? At point C is that pink one.
You gotta use my phone.
Are you kind of okay with those?
So like straight.
Okay, kids, let's talk real quickly about all these slopes. Okay? See the two diagonal lines that we have there? This diagonal line is representative of the equation where it says y equals what here?
X.
X. So what slope is really there?
Wait, no.
Y equals how many x?
1,
So the slope's really what value? 1. So this is really 1x for slope. So this slope is this one right here. I might make a note here. Well, it's a slope of 1. How about this horizontal one right here? What slope is that? Yeah, it's horizontal. So the slope on this line, this horizontal right here, is 0. Now, guys, I'm just talking about those 3 tangent lines that I drew in there: f prime of A, f prime of B, and f prime of C. The slope of AB is a solid line that connects A to B. And then 1 represents this dotted line right here, and then 0 represents this dotted line up top. So we've got to order these from least to greatest. So kids, I got to be honest with you, all those slopes appear to be positive except for what? The 0. So what has to be the least value here, kids? Letter F, right? So isn't F going to be the least? Okay, so let's just start looking at the slopes of everything. What's the lowest slope beyond 0 then? C. Okay. How about the next lowest slope, or the next? I guess start talking about increasing slopes. So B would be next, wouldn't it? Okay, so we've got. I'm going to cross these off. We've got the slope at B, slope at C, and slope 0 gone, right? Why D?
Because AB is.
We want to continually get steeper, right?
Yeah.
So AB would be the next one in order, wouldn't it? So it would be a D. What's after that? E, you say?
Yeah.
And then what's the steepest one? Okay, so kids, I want to point out, if you see notation like this, f prime of A, is that the slope between 2 points, or is that a slope that's at a point, or instantaneous point, or instantaneous rate of change? Did I draw a tangent line or connect 2 points here? Tangent line, so it's going to be an instantaneous rate of change. So you want to look at those slopes tangent to that. It just touches that point right there, and that's it, okay? Now, do those lines drawn in there, A, B, and C, help you visualize that? But you can kind of see that, you know, you can kind of visualize that. You don't really have to draw it in there. You're like, ooh, that slope at B has to be steeper than at C, because this curve's starting to flatten out, isn't it? Does that make sense to you? Okay. This is a pretty important concept right here. If you can visualize this and understand this, I think you're in good shape. So, kids, I'm done here recording today.